In this video, we'll study sequences and their limits. This lecture will be structured as follows. First, we'll define what a sequence is. I'll show you some examples. In the second part of the video, we'll study the concepts of convergence of sequences. So what is a sequence? A sequence is simply a real valued function which is defined on the set of all natural numbers. So you can think of a sequence as a map which is taking the set of all natural numbers into the reals. So a of 1 is going to be the image of 1 through a of 2 is the image of 2 through the function a of k is going to be the image of k through a, and then it keeps going forever, indefinitely. Now we'll introduce a special notation for sequences. So a sequence will be denoted as follows: a of k, where k is going from 1 all the way till infinity, or sometime we'll write just a of k. K is the natural numbers, or sometime, if it's clear what the context is we simply just write a of k, where the index k is assumed to be running through the set of all natural numbers. Alright, so perhaps we should now look at some examples. Let's suppose let's say n, where n is going from 1 all the way till infinity. Notice here that I can use whatever index I want. N or k is a dummy variable, so our index is usually going to be either k or n, but it could be anything, of course. Alright, so let a n, where n is going from 1 to infinity, be a sequence such that, now I'll tell you what the term of the sequences are. an is equal to 1 over n. So a1 is going to be 1 over 1. This is called the first term of the sequence. a2 is going to be 1 over 2. This is the second term. And we can, of course, keep playing this game indefinitely. A k is going to be 1 over k, and this is called the kth term of the sequence. One way to visualize what the sequence looks like is to look at how the terms are occurring on a real line. Okay. So suppose this is the real line. Now the first term of our sequence is 1. Let's put 1 somewhere here. Right, so we'll have a1 is 1. Then the next term is going to be half. That's a2. Then we have a third, and so on. And you can see that the term of our sequences are getting closer and closer to 0, but they actually never reach 0. Okay, we'll later see precisely how to understand the behavior that's going on around the real number 0. In the meantime, let's look at another example. Let an be a real value sequence, be a real valued sequence whose terms are described as follows. An is 2n plus 1. Okay, so now, of course, the first term of the sequence a1 is 2 times 1 plus 1, which is 3. The second term a2 is 2 times 2 plus 1, so that'll be 4 plus 1, right, which is 5. A3 will be 7, and it keeps going like that indefinitely. So indeed, this is actually this sequence is the sequence is a sequence. It's a sequence of odd natural numbers. Right, so essentially you recover all odd natural numbers except 1. So it's a sequence of natural numbers. Here's another example. Let an be a sequence defined as follows. An is equal to 2 over 3n minus 1. So one can see that the first term, a1, is 2 over 3 times 1 minus 1. That would be 2 over 2, which is 1. Verify that a2 is 2 over 5, and so on. A3, the third term of our sequence, will be 1 over 4, and so on. Here's another sequence. This sequence is actually pretty famous. It's known as the Fibonacci sequence. Let an be the Fibonacci sequence. What is that? It's defined as follows. It's defined recursively, right? So the terms satisfy the following recurrence relation. A1 is 1, A2 is also 1, so you're giving the first two terms of the sequence. Now the n plus 1 term is given in terms of the nth term and the n minus 1th term. It's precisely an minus 1 plus an. So the third, just because based on this definition, then you can compute what the third term of the sequence is, right? It's going to be a2 plus a1, so that'll be 1 plus 1, right, which is 2. The fourth term is going to be a2 plus a3, so that'll be, right, a2 is 1 plus 2, 3, and so on, and you can keep going forever. So even though you are not given explicitly what the kth term of a Fibonacci sequence is, you have enough information here to write down essentially, or to capture the entire behavior of a Fibonacci sequence. We'll come back to this type of sequences which are implicit, which are defined through some recursive relationships. Now let us turn to the concept of convergence of sequences. Intuitively, a convergent sequence is a sequence that tends to have a finite limit. Now this is of course not a precise definition. It's not good enough for the purpose of this class. So instead, let's try to provide a formal definition of what it means for a sequence to be convergent. Well, first you need a sequence to converge to a real number. So let A be a real number. We'll say that a sequence is convergent to a real number a, and we'll write that the limit of an as n is approaching infinity is a, when given any positive epsilon, there exists a natural number n such that as long as little n is greater than big N, then the nth term of the sequence is in the epsilon neighborhood of A. What does that actually mean? Now I'll try to strengthen your understanding of this formal definition by illustrating what is really happening. So let us try to visualize a convergent sequence on the real line. Right? So this is the real line, and let's suppose that you have a sequence which is somehow convergent to the real number A. Now you pick any neighborhood, any epsilon neighborhood of A. It doesn't matter how large the radius of this neighborhood is. So suppose you fix an epsilon, right, which is positive. So this will be A minus epsilon here, and this will be A plus epsilon. And what's in yellow is essentially representing the epsilon neighborhood of A. Now, if you have a sequence which is convergent to A, what is happening is that perhaps, let me change colors here. Perhaps the first term could be here. Maybe A1 is there. Okay, and maybe A2 is here, and maybe A3 is here, and so on. But the fact that the sequence is assumed to be convergent means that eventually you will find some natural number n, so that once you pick a term of a sequence which is coming after the nth term of the sequence, every single term will be trapped in this bubble. So there exists a natural number. So there exists a natural number n, such that an plus 1 will be here, an plus 2 will be here, an plus 3 will be here. Essentially, the nth tail of the sequence is contained in the epsilon neighborhood of A. So in other words, what this is really saying is that given a prescribed value epsilon, you can find a natural number n, capital N, large enough, which may depend on epsilon, so that the distance between the nth term of the sequence in A is no more than epsilon. I will later try to provide you with some concrete examples on how to actually use this definition. But before that, let us try to lay down some technical concepts. First, let's clarify a few things, a few terminologies here. Okay, so we'll say that the sequence an is convergent, and call A the limit of the sequence. If a limit doesn't exist, if a limit of a sequence doesn't exist, or if a sequence is not convergent, if a sequence is not convergent, meaning it doesn't have a limit, we say that the sequence is divergent. So there are actually two type of possibilities when you're given a sequence, right? So first, you can have, given a sequence, you can have that so you can have that either the sequence is convergent, or you could have that the sequence is divergent. Alright, so in the case where the sequence is convergent, then it always has a finite limit. If the sequence is divergent, there actually are two possibilities. Either it has an infinite limit, so the limit could be either plus or minus infinity, or it could actually have no limit. In either case, we shall say that the sequence is divergent if it either has an infinite limit or has no limit. Before we come back to some concrete examples, let us study some properties of convergence. The first property that we'll look at is the uniqueness of limits. And the point here is that if a sequence is convergent, then it converges to a number. And whatever that number is has to be unique. So, in other words, it is not possible for a convergent sequence to converge to two distinct real numbers. So let us prove this. Let us assume by contradiction that there exists a sequence which is convergent to two distinct real numbers, let's say A and B. Without loss of generality, let us assume that A is strictly less than B. Okay, so before I proceed with the formal proof, let us do some scrap work. Okay, so remember, this is not part of the formal proof, but still, it's essentially, I'm trying to intuitively explain to you what I'm about to, how I'm about to use, how I'm about to proceed by contradiction. So we're assuming that we have a sequence which is somehow convergent to two distinct real numbers. Let D be the distance between A and B. So D will be the absolute value of A minus B, right? Okay. So now we can pick a bubble small enough around A, right? And then we can pick another bubble small enough around B so that those two bubbles don't somehow overlap, right? So essentially, I want to find a neighborhood around A and another neighborhood around B, so that those two neighborhoods don't overlap. So to make sure that these two neighborhoods don't overlap, it is enough for me to pick this to be a d/3 neighborhood around A. I just need the radius of this neighborhood to be less than d/2. So I could have picked d/4, d/5, or whatever. As long as the radius of the neighborhood is less than d/2, we are fine. And again, here we'll pick a d/3 neighborhood around B, right? And now the point is, remember that we said that a sequence is convergent if and only if somehow you can find, for any epsilon neighborhood around the limits, you can trap a tail of the sequence inside that neighborhood. So because we have convergence, then somehow there exists a tail of our sequence which is trapped in the first neighborhood, and there exists also a tail of our sequence which is trapped in the second neighborhood around B. And somehow, since those two neighborhoods don't overlap, we have to get a contradiction. All right, so that's the big picture behind this proof. So since, now returning to our formality here, since the limit of an as n is approaching infinity is A, and also the limit of an as n is approaching infinity is equal to B, and there exist natural numbers n and m such that if little n is bigger than n, then an is sure to be in a d/3 neighborhood of A. And similarly, if little n is bigger than m, then we're sure that the nth term of our sequence will be in a d/3 neighborhood of B. Now let R be the maximum of n and m. So if we pick whichever is the larger in between these two numbers, assuming that k is bigger than R, we should obtain that AK is in the d/3 neighborhood of A, and at the same time the same kth term is also in a d/3 neighborhood of B. So in other words, AK belong to the intersection of these two neighborhoods. Okay. So now to complete the proof, we just need to prove that that this is absurd, right? So that these two neighborhoods don't overlap as illustrated previously here. But an illustration is of course not a proof. Let us be very precise about this. So the point is that since AK is in this neighborhood of A, then the distance between AK and A has to be strictly smaller than d/3, And since AK is in a d/3 neighborhood of B, then the distance between AK and B, has to be less than d/3. Now, what we really have, if we call this here star and call this double star, star is actually equivalent to the fact that negative d/3 is less than AK minus A, which is less than d/3, and double star is equivalent to the fact that negative d/3 is less than AK minus B, which is less than d/3. Now we'll take this inequality here and then we'll multiply by negative. If you multiply by negative 1, it essentially becomes B minus AK, which is less than d/3 here. And I'll call this here triple star. Now we'll add star. Oh, okay, I'll call this here triple star, and I'll call this one here 4 star. Now we'll add 4 star to 3 star. So adding this to this gives, so simply add term by term, that negative 2/3D is less than B minus A, which is less than 2D/3. But however, D is B minus A, and so we're saying that B minus A, which is D, is less than 2/D/3, which is equivalent to saying that D/3 minus 2D/3 is less than 0, and this is equivalent to saying that D/3 is less than 0, which means that D must be less than 0, which is absurd, because we have so this contradicts the fact that it is assumed that D is strictly positive. So we reach a contradiction. Therefore, the claim is true. Let us now look at some conditions which are equivalent to our formal definition. Suppose we have, let A be real numbers, then all 4 of the following statements are actually equivalent. Let me list them. A sequence AN is convergent to A. For every epsilon which is greater than 0, there exists some natural number n such that if little n is bigger than capital N, then the distance between AN and A is less than epsilon. For every epsilon which is greater than 0, there exists some natural number n such that if little n is bigger than capital N, then AN is in the neighborhood A minus epsilon, A plus epsilon. It's in this open set. It should be natural number here. And finally, for every epsilon which is greater than 0, there exists a natural number n such that if little n is bigger than capital N, then the nth term of our sequence is in the epsilon neighborhood of A. So really, coming back to what we've discussed before, the idea here is the following. If a sequence is going to be convergent to A, if for any prescribed value epsilon, one can find a natural number capital N which is sufficiently large so that as long as an index little n is bigger than the natural number capital N, then the distance between the nth term of our sequence in A is no more than epsilon. In other words, the distance between AN and A can be made as small as desired, provided that little n is sufficiently large. The part where we want the distance between AN and A to be as small as desired is captured by this inequality here. And the fact that little n is sufficiently large is captured by this inequality. So to prove again that a sequence is convergent, one needs to show that if you give me any prescribed value epsilon, I can find a natural number n such that this implication here holds true. The proof of this theorem is more or less pretty obvious. So because of that, I will leave it as an exercise. In fact, I will invite you to pause the video here and to take time explicitly to write down why all four of these statements are actually equivalent. Try to prove this for yourself. Make sure that you make your peace with this theorem before you move on. Now, it is important here to remember that the statement B, the B statement, is called the epsilon n criteria for convergence. And this criteria is known to be equivalent to our definition of convergence. Okay. All right. Let us now move on to an example. For our first example, we will prove using the epsilon n criteria that the limit of 1 over n as n is approaching infinity is equal to 0. So, I mean, that makes sense, right? If you take a sequence n, as n is getting larger and larger, you get 1/2, 1/3, 1/4, 1/5, and so on. And so the term of your sequence is getting closer and closer to 0. Now, how do we capture that using the epsilon n criteria? Let me show you first some scrap work, and then after the scrap work, I'll show you the formal proof. Remember, the scrap work is not meant to be a formal proof, so you should not, for example, in an exam or quiz, you do not show me your scrap work. Instead, you use your scrap work to organize your thoughts so that you can write a coherent formal proof. So let me show you. I'll write in blue my scrap work, and then I'll return to the formal proof later. So what we want to do here, right? We want to show essentially that for any epsilon which is greater than 0, there exists some natural number n, and this natural number will often depend on epsilon, such that if little n is bigger than capital N, then the distance between an here is 1 over n, and 0 is going to be less than epsilon. So I want to show the following. If you give me, so notice that here, this is the statement that we are trying to prove Okay, and these statements involve some quantifiers together with an implication. So, and you know how to prove an implication, right? First, to prove the quantifiers, to prove that, let me rewind a little bit. To prove that this statement is true, you want to show that if anybody give you an epsilon, you can find an n which depends on this epsilon. Okay, so that provided little n is bigger than big N, then 1 over n is going to be less than epsilon. Okay, so let me first look at my conclusion. Here's our conclusion. So notice that this is actually 1 over n. So this, if I call this here star, the conclusion here, if I call it star, then star is equivalent to 1 over n is less than epsilon. Okay, so we want to reach this, which is essentially means that we like to be able to, if you give me any epsilon which is positive, I would like to be able to find a natural number n which depends on epsilon, so that as long as little n is bigger than capital N, then 1 over n is going to be less than epsilon. Okay, all right, so now notice that this is true if and only if n is actually greater than 1 over epsilon. Okay, so then to make sure that little n, let me write this, to make sure that little n is greater than 1 over epsilon, it suffices to have that capital N is bigger than 1 over epsilon. And we know that by the Archimedean property this can be done, right? You know that by the Archimedean property, we can find a natural number n bigger than 1 over epsilon for fixed positive epsilon. Okay, so because of the Archimedean property, we can choose n to be sufficiently large, and we know that as long as n is big enough, we'll achieve our bound. All right, so this is the scrap work. Again, this is not a proof at all, but at this point my thoughts are organized, and then I can begin writing the formal proof. So to write the formal proof, let me switch back into the black color. So here is my proof. Let me go back again to what I want to show. I want to show all of this implication here. So I'll start by fixing some epsilon. So let epsilon be a positive real number. By the Archimedean property, we fix some natural number n such that n is bigger than 1 over epsilon. Now, to prove this implication here, now I want to prove that if this holds, then that holds. And how do you prove an implication directly? You assume the hypothesis. So I will assume now that little n is bigger than n. Assuming that little n is bigger than n, it is true that 1 over little n is going to be less than 1 over n, which is less than epsilon, since n is bigger than 1 over epsilon. So the distance between 1 over n and 0, which is 1 over n, is less than epsilon. So this is how you prove that for any epsilon I can find a capital number n, so that as long as little n is bigger than capital N, then the distance between 1 over n and 0 is no more than epsilon. This is the epsilon delta, the epsilon n criteria, and that's how you prove these statements. Let us look at another fairly simple example. We want to prove that the limit of 5 over n as n is approaching infinity is 0, or in other words, the sequence 5 over n. So in other words, the sequence 5 over n converges to 0. Okay, let's do some scrap work first. For our scrap work, we want to show that for any epsilon greater than 0, there exists some natural number n depending on epsilon, such that if little n is bigger than capital N, then the distance between 5 over n and 0 is going to be less than epsilon. So okay, note that it's actually just 5 over n. Okay, and to obtain that 5 over n is less than epsilon, it suffices to have that n over 5 is greater than 1 over epsilon. So we'll essentially solve this for little n, and this is equivalent to saying that n is greater than 5 over epsilon. And how do we achieve these bounds? Well, to make sure that n is greater, n is greater than 5 over epsilon whenever little n is bigger than capital N, it suffices to select n as a natural number such that n is bigger than 5 over 3, and this can be done by the Archimedean property, sort of similarly to what we've done earlier. Right, so the Archimedean property will allow us to find our capital N, which then will give us exactly what we want. Okay, this is the scrap work. Again, it's not the proof. Now, how do we write the proof? Now that my thoughts are organized, I can actually write a coherent proof. So proof, let epsilon be some positive real number. Appealing to the Archimedean property, we select a natural number n such that n is greater than 5 over epsilon. Now assume that little n is bigger than capital N. Right? So what that means, in other words, one over little n is bigger than 1 over n, and 5 over n minus 0, right, turns out to be just 5 over n, which is then less than 5 over capital N. Now, since little n is bigger than 5 over epsilon, then 1 over capital N is going to be less than epsilon over 5, and 5 over n is going to be less than 5 times epsilon over 5, which is epsilon. Thus, 5 over n minus 0 is less than 5 over n, which is less than epsilon. So we have proved indeed that for any epsilon, we can find some natural number n such that as long as big N is greater than 5 over epsilon, as long as little n is greater than, as long as for any epsilon which is greater than 0, we choose a capital number n which is greater than 5 over epsilon, and as long as little n is bigger than that fixed number n, then the distance between 5 over n and 0 is no more than epsilon. Alright, so let us prove now that the sequence 1 over n squared plus 1 is convergent to 0. Again, based on our scrap work, the idea here is really to prove that for any epsilon which is greater than 0, there exists a natural number depending on epsilon such that if little n is bigger than big N, then the distance between 1 over n squared plus 1 and 0 is no more than epsilon. Now, if you look at this inequality here, that's a tough inequality to solve for n. So instead of solving this inequality for n, we'll instead try to approximate the left hand side of our inequality by a simpler expression. So in any case, the distance between those two values is just 1 over n squared plus 1. Okay, and to simplify this, essentially we really want to make it as simple as possible by replacing this denominator by a simpler expression from above. That's the idea. So to make this fraction smaller, I'm sorry, to make this fraction larger, we just need to make the denominator smaller, right? So 1 over n squared plus 1 is less or equal to 1 over n squared. Another way of seeing this is actually as follows. One way of understanding is the fact that n squared plus 1 is greater or equal, in fact just greater than n squared, implies that the reciprocal of that is going to be less than 1 over n squared, right? So 1 over n squared plus 1 is less or equal to 1 over n squared, and the fact that n squared is greater than n implies that 1 over n squared is less than 1 over n, right? So 1 over n squared is less or equal to 1 over n. So this whole expression here is less than 1 over n. And to make this less than epsilon, which is what we really want, to make this less than epsilon, it is enough to make 1 over n less than epsilon. But to make 1 over n less than epsilon, it is enough to choose n to be bigger than the reciprocal of epsilon. And we know we can do this, right? We can because the point here is to make sure that n is greater than the reciprocal of epsilon. Whenever it is assumed that little n is bigger than big N, it is enough to choose n to be larger than the reciprocal of epsilon. And of course, similarly to the previous cases, this can be achieved by the Archimedean property. So that's our scrap work. Now let's write all of these formally. So for the proof, let epsilon be a positive number. Appealing to the Archimedean property, we may choose, or we fix, or we select a natural number n such that n is greater than 1 over epsilon. Now assume that little n is a natural number bigger and little n is bigger than n. Then the distance between 1 over n squared plus 1 and 0 is just 1 over n squared plus 1, which is less, in fact we can say here is strictly less than 1 over n squared, which is less or equal to 1 over n. And since little n is greater than capital N, 1 over n is going to be less than 1 capital N, which is of course less than epsilon, right? So in fact, instead of writing this, I can actually just write all of this here, and this is less than 1 over capital N, and this is less than epsilon, right? So we have proved the epsilon n criteria. So therefore the limit of 1 over n squared plus 1 as n is approaching infinity is indeed 0, and we are done. Alright, so now we want to prove using the epsilon n criteria that the sequence n squared minus 1 over 2n squared plus 5 is convergent to half. Again, first let's do some scrap work to try to organize our thoughts, and then we'll write the formal proof later. So again, we want to show that for any epsilon which is greater than 0, there exists a natural number n which depends on epsilon such that if little n is bigger than big N, then the distance between these two quantities is no more than epsilon. So let's first analyze the difference between these two quantities. First, using some straightforward algebra, one reached the point that n squared minus 1 over 2n squared plus 5 minus 1 half is actually just 7 over 4n squared plus 10. Okay, now let's try to, if you attempt to make this quantity here less than epsilon, you will want to solve this for n, right? But this involves solving an inequality involving a quadratic expression here, and this is a rational expression overall, and then you have a quadratic on the denominator, and that can be tough. So instead of doing that, let's make our job a little easier by estimating this expression from above by a simpler expression. Okay, so notice that 7 over 4n squared plus 10 is less than 7 over 4n squared, which is less than 7 over n squared, which is no more than 7 over n, right? And now to make 7 over n less than epsilon, it is enough to make sure that n is greater than 7 over epsilon. All right, so we have all our scrap work now, so let's write the proof, the formal proof. All right, so formally, let epsilon be a positive number. Using the Archimedean property, we choose a natural number n such that n is greater than 7 over epsilon. Now assume that little n is bigger than capital N. Now we'll have that n squared minus 1 over 2n squared plus 5 minus half. This will be common denominator will be 2 times 2n squared plus 5. And you have 2n squared minus 2 minus 2 n squared minus 5. Of course, these two cancel each other out, so we get 7 over 4n squared plus 10. Next, since little n is bigger than n, we'll have that 7 over 4n squared plus 10 is, of course, in fact since I would say since 4n squared plus 10 is greater than 4n squared, then this will be less than 4n squared, and this is greater than n squared, which is greater or equal to n, right? So this will be then less than 7 over 4 over n squared, which is less or equal to 7 over n. Now notice that this is bigger than capital N, right? So this will be less than 1 over n, 7 over n, which is then less than 7 times epsilon over 7, which is epsilon. See? So we have proved again that if you give me any epsilon, I can find a natural number n which is big enough, and the idea here is to choose n to be bigger than 7 over epsilon. And as long as you know that, then you're sure that the distance between n squared minus 1 over 2n squared plus 5 and half will be no more than epsilon. Therefore, the limit as n is approaching infinity of n squared minus 1 over 2n squared plus 5 is indeed equal to 1/2. Now I want to come back to a concept that I have introduced sort of briefly without formally defining it. It is that of an M-tail. So what is an M-tail of a sequence? Well, let M be a natural number. The M-tail of a sequence AN is a sequence of real numbers AM plus 1, AM plus 2, AM plus 3, and so on. And we will often denote the M-tail of a sequence as shown here. Now, as in the illustration, if this is a sequence, you have A1, A2, A3, and so on. So this keeps going till eventually you get AM. Now, we'll call this the head, the M head of the sequence. What happens if we remove the M head of our sequence? Then we get the M tail. So this will be AM plus 1, AM plus 2, AM plus 3, and so on. Right? So this here will be the M tail of the sequence. Our next result says the following. Let M be a natural number and let AN be a sequence of real numbers. Then the sequence AN is convergent if and only if its M tail is also convergent. So an interpretation of this result is really that you do not change the convergence of a sequence by eliminating a finite number of terms. Okay? Alright, so let's prove this result. Okay, so to prove this result, because this is a biconditional statement, there are really two things to prove. So first, let us assume that an is a convergent sequence. Now fix epsilon, fix a positive number epsilon, then and choose n, which is a natural number, such that an is in the epsilon neighborhood of a. So we assume here an is a convergent sequence and its limit is some real number a. So we fix an epsilon, and then because we know that our sequence is convergent, we can choose a natural number such that an is in the epsilon neighborhood of a whenever, of course, n is bigger than bigger. Alright, next, let n prime be the maximum of the sets containing n and m plus 1. Alright, then whenever little n is bigger than n prime, then we know that n, right, will be, of course, and here n is going to be bigger, or at least m plus 1, and because n prime is at least big N, then by assumption an is in an epsilon neighborhood of a. Okay, so all terms of the sequence the n-tail sequence belong to an epsilon neighborhood of a whenever little n is bigger than n prime. Therefore, the limits of the m-tail sequence, is convergent to a. Now for the converse, let us assume that the n-tail sequence convergent to some real number a. Now let epsilon be a positive number. By assumption, there exists some natural number n which is going to be greater or equal to m plus 1, such that an is in an epsilon neighborhood of a whenever little n is larger than n. This implies that there exists some natural number n such that an is in an epsilon neighborhood of a for any little n bigger than n. Consequently, or as a result, okay, thus an converges to a. Our next result is known as the Squeeze Theorem, and is stated as follows. Let L be a real number and let A and Bn and Cn be three sequences, satisfying the following compound inequality. An is less or equal to Bn, which is less or equal to Cn for every natural number n. So essentially Bn is sitting in between An and Cn. If the lower bound and upper bound sequences are both convergent and converge to the same limit, then the sequence in the middle has to also converge and must converge to the same limit. So the idea of the proof is as follows. So let epsilon be a, so first let us assume that An and Cn are convergent to L, and let epsilon be a positive real number. By assumption, we may choose fix natural numbers a and c such that if little n is greater than a, then the distance between an and L is less than epsilon, and if n is greater than c, then the distance between C and N and L is less than epsilon. Okay, so now let's let n be the maximum of A and C, and assume that n is a natural number such that little n is bigger than n. Then because n is both bigger than A and C, we'll have that negative epsilon is less than An minus L, which is less than epsilon, and this is equivalent to saying that L minus epsilon is less than An, which is less than L plus epsilon, and similarly negative epsilon is less than Cn minus L, which is less than epsilon, is equivalent to saying that L minus epsilon is less than Cn, which is less than L plus epsilon. Now coming back to this, now we'll exploit this inequality here. So thus we have that negative epsilon plus L is less than Cn, no, An first, sorry, An first, and An is less or equal to Bn, which is less or equal to Cn, and we know that Cn is less than L plus epsilon when n when little n is bigger than n. Now we'll just focus on this part of the compound inequality. In other words, negative epsilon plus L is less than Bn, which is less than L plus epsilon, and adding subtracting L everywhere gives that negative epsilon is less than Bn minus L, which is less than epsilon. Therefore, the distance between Bn and L is no more than epsilon when n is assumed to be bigger than n, which is the maximum of A and C. In conclude, so we have proved. Consequently, the limit of Bn as n is approaching infinity is going to be equal to L, and we are done. Our next result says the following. Suppose you have a sequence of real numbers, an, and let's see be any real number. Then if an is convergent to 0, then c times an will converge to 0 as well. The second result says that if the limit of an is a, which is a real number, then this is true if and only if the limit of the absolute value of an minus a is convergent to 0 as well. Alright, I will leave the first part of the theorem as an exercise for you. So pause the video and try to prove for yourself that a is true, and I will prove here that I will offer a proof for the second part of our result. Alright, so I will only focus here on B. So there are two things to prove again. So assume here that the limit as n is approaching infinity of an is equal to a. Now let epsilon be a positive number. By assumption, we may choose some natural number n such that if little n is bigger than big N, then the distance between an and a is going to be made less than epsilon. Okay. However, note that the quantity an minus a minus 0 is precisely equal to the absolute value of an minus a, right? Which is then so thus noting that, let me rephrase this a little bit, noting that this hold, then we can see that an minus a, the distance between this quantity and 0 is less than epsilon whenever n is larger than capital N. Therefore, the limit of the quantity an minus a as n is approaching infinity is going to be in fact 0. Now for the converse, let us assume that the limit as n is approaching infinity of an minus a is 0. Now let epsilon be a positive number, or given some positive number epsilon, let n be a natural number such that let n be a natural number satisfying the following conditions. If little n is bigger than n, then the distance between an and a and 0 is less than epsilon. Noting that this quantity here is actually just right. It follows that, let me call this here star. Star holds if and only if the absolute value of an minus a is less than epsilon. Whenever little n is bigger than n, we have that an minus a is less than epsilon, and we may conclude that the limit of an as n is approaching infinity is a, as desired.